Thank you again. So my name is Cipriano, and today I will give you a categorical account of the setoid model. So this talk follows the one given yesterday by Emilio and Pietro, in which they presented the minimalist foundations and some results within the minimalist foundation. So for who was not here yesterday, just a quick recall. That is, the minimalist foundation is this foundations of constructive mathematics ideated by Mayet and Sambin in this work, and then fully formalized in this work of Milli. And it consists of two-level foundations in which we have an intentional level, which is an intentional type theory that will be denoted with MTT during this talk, and an extensional level, which will be denoted with EMTT for the rest of the talk, which are, let's say, separated, okay? But we know that extensional type theories have those extensional constructs such as functional extensionality, uniqueness of identity quotient types, which make them more suitable for formalizing mathematics. But intentional type theories have those good intentional features such as canonicity, normalization, feasibility of type checking, which make them more suitable for proof assistant, for developing proof assistant. So what we want to do through the setoid is an implementation of the extensional level over the intentional one, just to take both the advantages of both the levels. Okay. So I'm going to recall how does it work, this implementation through the so-called setoid model. Okay? So let's start from the definition of setoid. So a setoid is just a pair where A is a type, in case of the minimalist foundation, a collection, which is a closed type, and R is a proposition, which is a type depending on A times, which is also an equivalence relation. So which is a setoid is just a type equipped with an equivalence relation. These are also called like a Bishop set, because bishops define a set actually as a pair like this in its foundations of constructive analysis. And the morphism of setoids is just an equivalence class of arrows, of terms, let's say from A to A prime, which respects the relation. So if we have the two terms of A are related, what we want is that the image of these two terms through F are R prime related. Okay? So this means that the arrow respects the relations. But we take an equivalence class of these terms given by the following relation. We have the two terms are in relation if and only if they have the same image with respect to the relation of the codomain setoid. Okay? And from now on, I will denote with STD the category of setoids that is on the screen.
Can I ask a question?
Yeah.
The type theory that you're writing this in is the intentional layer. Is that right?
Exactly.
Okay. So is it proof relevant, the notion of proposition? Is it proof relevant or proof irrelevant?
The notion of proposition in the minimalist foundation is proof relevant.
So when you say equivalence relation, it's not a mere relation, if I'm speaking in the sense of set theory, extensional type theory, homotopy type theory.
It's not that.
It's actually a structure. The equivalence relation is a proof relevant type over the square of A.
Later we will see that
they give rise to
pseudo-equivalence relations.
There can be many terms that witness
the
fact that R is an equivalence relation. Even though it says R prop, we shouldn't think of that as -1 truncated or something.
No, absolutely. Okay. Thank you for
So it's like the structure of a graph, or something. It's a graph.
Exactly. Yes. Then we will see something more about this structure. If you are working with the Martin-Löf type theory, you can just consider R as another type, which is an equivalence relation in the sense that you have a term witnessing the reflexivity with another term for symmetry and another term for transitivity. But if I have that two terms of A are related, it doesn't mean that there is a unique way to state that they are related. They could be more proof term of the fact that they are related.
So it's like a groupoid structure,
Exactly.
but without the laws.
Yeah, that is the last point of the tour.
Sorry.
Yes, yes.
Don't mean to steal your thunder. Just want to understand.
Yeah, it's very interesting. It's very interesting what you say. I find it really interesting. So but in order to implement this, to implement extensional type theory to the intentional one, just setoids, non-dependent setoids are not enough. We need to also to explore a notion of dependent setoids. And like last week, this is probably that part of setoid theory which someone last week was referring to the setoid. But I hope that at the end of this talk, you will find setoids and dependent setoids a little bit nicer, but it could also happen the opposite. So let's see at the end of this talk. So given a setoid, we define a dependent setoid on these setoids just with a triple B S sigma. And it is useful, I think, to draw the picture of the syntactic definition that is going to appear on the screen. So what we are requiring, a base type A, and for every term of A, we are requiring a type B of X. Okay? Then what else?
Sorry, I have a question.
Yeah.
Is call just the time-oriented type?
Yeah, it's, so also Peter was telling you yesterday that call is like a kind of type in the minimalist foundation.
Okay.
So if you want to, you can read this for like in the Matilov type theory and see type. Okay, just the judgment that is a type. But now with the pose, it's a little bit uncomfortable because what we need is also a dependent equivalence relation on the type B. Okay, and I will use F minus 1 and TR for the terms witnessing the equivalence relation, and also a sigma, which depends okay, which is a term from the type B of X. So the type B of X prime, which has some features. Namely, the first one is that if we cannot see that. Okay. The first one is that if we have a witness of the fact that two terms of B are S related, where S is the relation non-B, so we have Y prime, and the relation Q, what we require is that the image through sigma are S related in B of X prime. Okay? So what else? We also want that the action of sigma on the loop given by the reflexivity term is actually the identity function on B of X. And we also require this sort of transitivity, which means that if we have another proof term of the relation between x1 and x2, but we could have also a proof term of the relation between x and x2. Here we have the composition of two sigma, and below we have the sigma given by a proof term between, of the relation between x and x2. What we require is that the image of this path is equal with respect to S to the image of this other path. Okay? Sorry, pause there. Okay, this is the third condition. And look that we are not requiring this term to be the transitivity. I'm just saying if we have three of this form with this domain and codomain, this should happen on the fibers of the setoid. And with these three axioms, what we can prove is that actually the transport map sigma does not depend on the proof term that you are using, which means that if you have another proof term stating the relation between x and x prime, sigma of p and sigma of p prime actually have the same image with respect to the relation S. Okay? So in order to do that, in order to get familiar with dependent setoids, I want to see how do we interpret, for instance, the arrow type. Okay? So, if we have a closed type A and two dependent types B and C, and we have already interpreted A with the setoids AR, B with the dependent setoids, this one, and C with this other dependent setoid, how are we going to interpret the arrow type? So, here, the non-bold characters live in the extensional level. The other one are living in the intensional one. Okay? So, the base type of the dependent setoids for the arrow type is simple. You just take the arrow type between the base type of the two dependent setoids. But then we need to put a relation on the arrow type. And what do? Is to say that two functions in the arrow type are related if they have the same value with respect to the relation in the codomain of the setoid. Okay? But we also need to define the sigma, which is a transport from B to C over X and B to C over X prime. And what do? Is just to compose the transportation, the transport arrow in the opposite direction. We apply F and then we apply the transport arrow of C. So we are using the transport arrow of B, the transport arrow of C, and an arrow that we want to transport. So we define the transport of F as this composition. Okay?
Sorry, moving your question, but you say that the normal characters, the sans serif characters, live in the extensional level?
Exactly.
The bold live in the intentional level?
What?
The bold ones live in the intentional.
Exactly.
What about the inequalities?
The
equal signs and the parentheses.
That's a definition. So it's an inductive definition. So assume that you have already interpreted this as this setoid. Assume that you have already interpreted the type B as this dependent setoid, and assume that you have already interpreted C as this dependent setoid, then you define the interpretation of the arrow type as this dependent setoid.
Okay, so it's in the meta-meta level.
They live here in this room. They live here in this room.
Okay.
Those equalities.
Yes, okay.
Should the second y prime be 1?
Yes.
Yes. Okay.
Y primo e y. Y primo lì.
Yes, this is why. Yeah, thank you. Okay, so let's go on. Let's see something else. So you know that in the minimalist foundation we have okay, I see something on the screen which is not there. It's fine. We have this different kind of proposition. So how we are going to interpret proposition of the extensional level into the intensional one? In the extensional level, proposition have the property Steve was referring to before. So if we have two terms of the proposition, they are equal. Okay. So how we are going to, which is the uniqueness of the anti-proof, how we are going to implement this in the setoid model? We just interpret propositions as dependent setoids in which the dependent equivalence relation is the total relation. Okay? In this way, what we are going to do, for instance, for the identity type of A, we are going to interpret the identity type of A as the relation of the setoids which has interpreted A. with the total relation. So in this way we obtain the uniqueness of identity proof, because now every two terms of the identity types are equal with respect to the relation of the interpretation. Okay? And a similar way, since we are interpreting a proposition in this way and the arrow type in the way of the last slide, we obtain also the functional extensionality. Because if we have a term of the fact that two arrows, two terms, have the same value, we can extract a proof of the fact that they are equal with respect to the interpretation of the identity type of the arrow type. Because actually what we did was to take as the interpretation of the relation on the arrow type, the functional, this functional equality.
What is TR again?
TR, yes, thank you. I brought TR because, I mean, when I give you a dependent setoid, I should give you the sigma. So if you try to write the sigma for this dependent setoid, you have to use the transitivity.
Okay.
So if we, later we can see, if we try to see how sigma works, you use the transitivity of R to build the transport R. That's all. Thank you. So the last one is the quotient type. It's a little bit more difficult, but it's very intuitive in the sense that if we have a dependent type and another relation, in case of the minimalist foundation, we take sets and small proposition, and S tilde is a small proposition on B. Supposing that we have already interpreted these characters, here we have the top because this is a proposition, how we are going to interpret the quotient? The quotient is just the interpretation of B where we replace the relation S of B with the new relation, the interpretation of the new relation. If you go to, if you enroll all the definition of S tilde, what you see is that S tilde is actually bigger than SB. And the transport works also for S tilde. So for the quotient, you just need to update the relation of the quotient of on your dependent setoid. Okay, so this is the way in which we interpret type. I didn't mention how to interpret terms, but it's very intuitive once you get the interpretation of types. And it looks that it's almost done, no? But there is an additional difficulty, which is the extensionality. Because what we are doing is to interpret an extensional type theory into the intensional one. So in particular, we want to validate the reflection rule, which says that if two terms are propositionally equal, they are actually judgmentally equal. Okay? So we cannot interpret the I here with just a pre-interpretation. Then we have to take a quotient, to take equivalence class. Okay? And what we do is to define a suitable equivalence relation on the interpretation, and for instance, we should, in this case, identify these two interpretations. But if you have this relation, you can use the substitution rule, and you take that every type depending on A is equal to every type dependent on A prime, if they are equal. And this gives you an additional condition on the interpretation, because you need to identify all the dependent types, okay? So what we do is to quotient also these two interpretations. And one could think that, okay, it's done, you just need to care about this. But actually what happens is that there are many other quotients that one should do, because they are implicit. If we have identified these two guys, and we have, for instance, the arrow type, we have to identify also these two interpretations, okay? And so on and so forth. So
this is happening now, again, in the meta language. The identifications are not in the theory, either one of the theories. They're kind of external definition of the interpretation, is it correct?
yes, but how do we define this relation?
You still have to be setoid.
Through canonical isomorphisms. Okay, this is the solution to take into account all these quotients that one should do. And so this is actually the real phase of the full interpretation. We need to create a quotient or a relation through canonical isomorphisms, which are defined inductively. And this is the way in which you can manage to obtain all these identification that you need to take the extensionality of the interpretation. And there are these two references, the work of Milli, which is all that I'm saying is in this work of Milli, the minimalist level foundation, but also you can read about Hoffman PhD thesis, because he also was used to work with setoids a little bit different from those that I'm telling you, and with the canonical isomorphism.
When you say that the identifications aren't happening in the original theory, I thought that you have this extensional layer which has equality reflection as a rule, right? And that's why you're doing this. So,
well, we're trying to show that the interpretation is sound with respect to those rules. We've defined an interpretation of the extensional theory, and now we need to show that it satisfies the rules.
so you're saying that, like, well, all the previous stuff, this I function, it doesn't satisfy this rule, but it would satisfy all the other rules. And so this is like an interpretation of like UIP and lots of other rules, but not
of the reflection.
Of the reflection.
Exactly. So actually what we do is to take the interpretation as the class, for instance here, of the terms that satisfy what you need up to canonical isomorphisms, which are defined inductively. Okay.
Are you going to show how you...
No. That is very the difficult part for me of the interpretation.
So let me ask then, do you end up having like everything in the intentional level?
Yeah, because you can define the equivalence classes. No, you can, in a proof of system you would say, okay, the extensional type is an equivalence class. I mean, are some types up to the following relation.
How do you write it up to?
And you say with canonical ISO, which can be defined internally to the intentional level.
But are you combining things that have the same types? I mean, like, it seems like this might require you to talk about elements that are formally like no longer like type correct in some sense.
That's what
The implementation is not done at all, no?
Formally, you do a H category alla Palgram. The notion of H category in a theory.
Which is an intentional type theory. So you have a type of objects, but the type of object, of homomorphism between objects as a relation, stays when they are equal, and everything is done within the intentional level. So it's not something, a quotient given at the meta level. Everything can be stored in the intentional one. Okay?
It's a further layer of setoid health. We're descending into the
Plateau. Now we move into the categorical paradise, if you want to. So this was the syntactic account of the interpretation, but what we are interested in, at least for me, is very interesting to provide a categorification of this setoid model, and in the sense that we are going to use some tools from category theory, such as operation, in order to describe all these operations that I have told you, but not up to canonical isomorphism, in the sense that we have not yet developed something for canonical isomorphism in categorical terms, which is a very difficult task. But up to the interpretation, so the formalization of setoids, the implementation of the interpretation of the type construction is something that you can do using category theory. Okay, so we want to provide an algebraic description, which gives also a verification of the setoid model, and it relies on the fact that in the history of setoids, people have thought about them as a quotient completions of equivalence relation, because we are just taking a type and we are quotienting terms with respect to the relation that we are putting on the setoid. And it is well known that if you take, for instance, the Martin-Löf type theory, and you take a suitable category of closed types, and you provide the exact completion, the exact X-weak X completion, what you obtain is the category of setoid. Okay? But let's see how it works, this exact completion of a weakly lex
Sorry,
or
the
a lex
category of
category.
setoids inside of multiple theory.
Yes.
Okay. Yes. And this is important for what I'm going to say. Because what is how does it work, the exact completion? This work was developed by Carboni and Celiamagno for the left exact categories, and then was improved by Carboni and Vitale for weak left exact categories, which means that you have weak limits, definition of weak limits instead of limits. And what they did was to consider pseudo-equivalence relation. So pseudo-equivalence relation in a category is just a pair of arrows which have an arrow stating the reflexivity, one for the symmetry, one for the transitivity, which should satisfy all the rules that you expect. But notice that they do not require in the pseudo-equivalence relation this pair of arrows to be jointly monic, which is something related to what you were mentioning before. Okay, so that is the point. Why we don't take a jointly monic pair of arrows? Because we could have more witnesses of the fact that two terms are equal. In particular, in the case of closed type, this should be the pseudo-equivalence relation arising from a relation on the type A. Okay, so these are not jointly monic because here we can have two witnesses of the fact that they are related with the same domain and codomain, something that you can figure out if you try to write these 4 types. So,
Yeah, just a really simple question. What's the little star or like sun?
the sun. Okay, this is my tactic. There, I should remember to tell you something.
Okay, now I have a question. Not every pseudo-equivalence relation is of this form for a dependent type R. There could be other maps.
Exactly.
So what do you do about that? Because when you make the setoids in a type theory, you're really only working with the dependent types.
Exactly.
You're not working with the real exact completion of the category. Is it correct?
Yes,
Equivalent.
but
It's equivalent.
exactly for
It's
at least
equivalent.
for this case, it's equivalent because if I have something like this,
Yes.
I can obtain a dependent type. No, just taking.
That's fine, yeah.
Okay.
But what if I have something of the form B, T,
No, that's
S
sorry.
going to A?
Exactly. Let's
Then
say
you
something
need
like
sigma
this.
type and identity type and.
Something like this,
Yes.
where R is a closed type. I can build a dependent type on the top of this. So
it won't be the same. It will.
Exactly. They are equivalent.
Equivalence of the category.
That's a question.
Yeah, they are equivalent.
Okay.
Yes. And so what Carboni, Celiamagno, and Vitale proved is that this construction is the free exact completion of C. So it has a good categorical property that I'm not going to recall. But after this, one can say, okay, we are done. So we have the description of setoids in a categorical version. But the point is that we are assuming here to work in a sort of, in the paradigm proposition as types, in the sense that we are not distinguishing relation if they come from, if you have a different kind like proposition, like in the minimalist foundation. So in the minimalist foundation, you don't want to take all the relation, but just those coming from the kind of proposition. So you want to like take to customize this construction just for the relation that that represents your logic, okay, which come from your logic. And what Mimmi and Pino did to face this problem in a very general context was to introduce the elementary quotient completion. So the elementary quotient completion, here we start to see the use of vibration, because these are controvariant functor into the category of ink semilattices, which correspond to preorder vibration, which you have to think like C as the category of context and the values of P as the propositions on your context, okay, let's say. So we just require C to have finite products, and we C to have finite products, and for every object, the existence of an element in the fiber over A times A, which plays the role of your identity, okay, of equality. And this is formalized in Lavir. This is a definition from Lavir, which defines the equality as a suitable adjunction with a suitable left adjoint to array indexing, which is not shown here. So in this context, you can say, okay, I want to consider just P equivalence relations. So those elements in the fibers over A times A, which have in the internal language can satisfy the reflexivity, the symmetry, and the transitivity. And what you do is to provide a new doctrine, which is denoted with P bar, on this category of C bar. And as you may expect, the category of C bar is a category, let's say, setoids, because we have an object of the category C and a P relation on the category C. The arrows are defined more or less as for the setoid case. And we have on the fibers of a setoid the descent datum of the relation, which means you take the subfiber of P of A of those elements such that if you have B of x1 and x1 are related with x2, then you also have B of x2. And in this way, this is a free construction which adds P quotients, is let's say a P quotient completion, which was developed by Pino, Rosolini, and Milli to, let's say, describe the setoids for the case of the minimalist foundation. Here there is also something that I did during my PhD, is a slight generalization of the quotient completion, in which we don't require the category C to have products. The category C not to have products, but just weak. And as examples of this construction, you have a generalization of the exact completion. And in case of the minimalist foundation, you can build an elementary doctrine from a suitable category of closed types, and you can take the doctrine which gives you just the proposition up to equiprobability. And what you obtain is that the base category of the elementary quotient completion of this doctrine is equivalent to the category of setoids. So this is the way in which Pino and Milli managed to customize the exact completion in that sort of sense. Okay, so I think, how much time do I have?
Given that you started late, maybe 20 minutes.
Okay, so now we move to the last part of the talk, which is part of a joint work in progress with Milli and Samuele Maschio. So they had already the description of setoids, but I mean, at the beginning of this talk, I was talking also about dependent setoids. So a fiber version of the elementary quotient completion is, in the sense of this title, is to find, I mean, a suitable description of dependent setoids in a suitable fibered way, let's say. And this work, which is fiber sets within a predicate variant of Highland's effective topos, is the continuous, the second part of a previous work of Milli and Samuele, a predicative variant of Highland effective topos, in which what they did was to define the predicative effective topos, which is a category obtained, which is a strictly predicative variant of the Highland effective topos, which relies on the Pfefferman's theory of non-iterative fixed point CD1 et. So what they did was to construct within this theory a category C of R and to define controvariant functor of collection, which is isomorphic, whose Grothendieck construction is isomorphic to the codomain fibration, but they were also able to define a suitable subfunctor of realized sets. How they did it was because ID1 hat has the possibility to define a universe for the sets through, let's say, a fixed point of a suitable formula of ID1 hat. So what they did was to use an idea that probably they had already in this work with Ishiara and Thomas Streicher to define this universal set, which they used in order to define the collections on the category of on this category of CR. Okay. So what was the point? In their previous work, they proved a lot of properties of the category, the predicative effective topos, which is actually obtained as an exact completion of the Lex category of CR. And what you can do with the codomain fibration of this category is to give an interpretation of the collection, because their ultimate goal was to obtain a model of the extensional level into the predicative effective topos. The point was now, how do we interpret dependent sets? Okay, so this structure was already present in their work, and now we are working on, also this part was already present, we are working on this fibration, which is, as I told you, the fibration which concerns dependent sets to interpret dependent sets of the extensional level of the minimalist foundation. So, what was the idea here? Was to describe again dependent setoids as pseudo-groupoid action. We come back to the question that Steve made at the beginning of the talk. So there is a lot of category theory about action of groupoid, because you can see from this draw that a dependent setoid is a sort of groupoid action, in the sense that we have the relation on A acting on the types B of X. Okay, we have morphisms we behave well, and this kind of stuff look like an action of a groupoid. But for the reason mentioned by Steve, when we work with the equivalence relation in an intentional environment, what we get is not a groupoid, but something weaker, because for a groupoid you should be able to state the usual law, like for instance the unital law, and you don't have this kind of stuff when you use intentional relations, because no one is going to tell you that the transitivity of a witness of the fact that R relates X and X prime with reflexivity is equal to the first witness. This is something that you don't have for intentional equivalence relation. So what we did was to describe, let's say, pseudo-equivalence relation in a different way. And this is a very new, this is something very recent in our research, was to describe pseudo-equivalence relation as a two truncated simplicial object in the category in which we were working. So what is a two truncated simplicial object? It's just a contravariant functor from the two simplex to the category in which we are working. This defines an internal diagram of CR. And this has a very geometrical intuition. I mean, are you aware about this category delta? Is everyone aware about that? So, just who is not aware, just to say that this is a category in which we have just three objects that you can image like a point. Then we have another object given by hash of 0, 1, and then we have another object given by like a triangle of this form. Okay, more or less these things live in the two simplex. So what we do in this framework is like, okay, we have a pseudo-equivalence relation, we have a diagram. I mean, the object is A, this plays the role of the objects of your diagram. This plays the role of the arrows of your diagram, which is a sort of weak groupoid. And this plays the role of the composable arrows. Well, but we do not require the composition as following the groupoid law. In the sense, we just say when two arrows can be composed. Two arrows can be composed if there is just another one closing this sort of triangle. But this is becoming a little bit obscure. So let's try to figure out what is R2 in the case of an equivalence relation. R2 is just given by, let me write this type. This is our R2. We just take the triples of composable relation, like those that you see here. We just have a witness of the fact that x prime are related, another one for x prime and x2, and another one from x to x2. Okay? And this object, we can use these objects in order to define pseudo actions in the sense of this paper by Hermida, which is talking about the sense of two fibration, which is very more general, but we can just take something about the theory and we can explore this notion of pseudo action in the sense of Hermida. So why we do not use, for instance, this other very famous paper by Janelitz and Tholen in Physics of Descent, again, because they are working with internal diagram in CR, which look like categories or groupoids, or let's say in a strict sense. We need something weaker. So we adopt this other description of weak groupoid. And what we do with this, and now you can resemble, you can spot the similarities between these diagrams and these diagrams here, because what we take are these actions which are defined in this way. We take a fibration, in this case we take the fibration of sets equipped with a relation, and we took an object on the object part of the diagram. We take an arrow on the arrow part with this domain and this codomain, and then we take an equality on the two simplex part of the diagram. So if you look at this, we are just defining B with a relation. We are just defining a sigma, which respects the relation. And this one, this is 0, 1 of sigma, the reindexing over 0, 1. This is 1, 2, and this is 0, 2. And this is just what is written here. We are just stating that this path is equal to this path. And this is the equality on the two simplex object. And what we did with this definition, we collected these actions, this pseudo action, in a pseudo functor, and we obtained a fibration, which is the left on the screen. And we were able to prove that the category of the action over a setoid and the slice category of the predicative effective topos are locally Cartesian closed-list arithmetic pretopos, which is what we need to interpret the extensional level of the minimalist condition in the predicative effective topos. So, our future and current investigation is to provide a suitable universal property for the pseudo-descent objects that I showed you as a fiber quotient completion, so to give an abstract categorical property of this construction, and we hope near future, we want to obtain a formalization of the setoid model in a proof of system. Okay? And so this is what I wanted to tell you today. Thank you.